Unit 1, the alphabet and grammar of geometry, lesson 1.14, brain in hand problem solving. Taking a look here, make sure you get the date, time, location, as well as a parent signature sign-off. Once again, please don't attempt to multitask. Stay very focused. This is one of the most revolutionary and important preview notes of the year. It is a very, very important video introducing something called brain in hand problem solving. Please stay focused. Before we go into today's lesson, let's do a quick review. You're going to work on this page on your own without a calculator, and you're going to restart the video when you're done. Once again, do this on your own, then restart. Pause. Welcome back. Let's see how you did here. We cross multiply, not cross cancel, so we're going to go like this, and that's 6 times 9 equals 2x. Why didn't I multiply? Because the key to multiplying is not multiplying. It's factoring. Listen carefully. The key to multiplying is not multiplying. It's factoring. Watch very carefully. I'm going to divide both sides by 2. This makes it much shorter. Once we can get that number written, cancel that out. And then I come over here, and I see that that 2 and that 6 goes in, so 2 goes into 6 3 times. 3 times 9, x equals 27. The key to multiplying is not multiplying, it's factoring. See how you did for the algebra? Circle, distribute, circle, distribute. Collect terms. Divide out. And you should have gotten v equals -4. You can always plug it in to check. Basic algebra review. All right, let's get in today what we are learning. You're going to learn a lot of neurology today. Some very important vocabulary is in hand. You need to understand the concept of a neuron, which are the brain cells, the name of cells in your brain, as well as your spinal cord. Frontal cortex, the difference between a digital immigrant versus a digital native. Hypertext skimming, and something called linear reading. Let me give a little background. About 6-7 years ago, I started noticing a change in the way my students would attack problems. I would write a problem on the board, and it'd be a mere 2 sentences describing a diagram, and instantly my students would reply, "I don't get it." And I was a bit bewildered. Why were my students having such a hard time with what I perceived to be extremely simplistic problems? And I discovered over the course of a couple years study, and I did my master's thesis on this particular topic, that I, as what's called a digital immigrant, which means I did not hit digital technology to my young adulthood, versus you guys who are digital natives. You've had digital technology since you had pacifiers in your mouths, that it meant that our brains were wiring differently. And the difference in the wiring was creating distinct differences into how to attack math problems, which means there were certain things I perceived relatively easy and my students were finding to be increasingly difficult. This is what my master's thesis addressed. There are 5 key thoughts before I get into how brains are wired differently because of digital technology and then what we're going to do about it. These are key thoughts. Now, very important, both students and parents. Everything I'm saying right now may seem a bit like bizarre. It's very important that you see everything I'm saying is footnoted. You're welcome to explore these footnotes if you need clarification or the scientific research behind this. Step number 1, key thoughts, 5 key thoughts. The first key thought is simply that your fingers in general have neurons which physically connect them to your frontal cortex. Your frontal cortex is the conscious thinking part of your brain. That is the frontal cortex, the conscious thinking part of your brain. The occipital cortex is the visual part of the brain. In the middle here, we have what's called the motor cortex, which is both voluntary motion. And then you have the cerebellum down here below, which would be the involuntary motion and reflexes. So you need to understand that there are neurons connecting your hand to the thinking part of your brain. 2, technology and the use of technology is physically reshaping brains and neurological connections. Why is technology doing this? Because we are keyboarding now more than we physically write. We are clicking on stuff more than we physically color and shade. And we are tapping on screens far more than we are physically handling 3D objects. Because of this, because of our hands working in an increasingly digital realm, there is less and less input in those fingertips, and it is changing the way brains are wired. Once again, everything I'm claiming is footnoted. You're welcome to look that up. So key thought number 1, your fingers are connected to the thinking part of your brain. Key thought number 2, technology is physically reshaping how neurons connect in brains. Key thought number 3, this is super important. You may or may not have figured this out by now, but reading on a screen is different than reading in print. Again, it's been footnoted. When your eyeballs hit a screen of any kind, an iPad, a tablet, a laptop screen, our eyeballs have a tendency to go in hyperskid mode. We just kind of wander down the screen. We do not read for details on screens in general. We automatically default to hyperskimming, whereas when we're in printed, especially when you add the finger on the paper, we tend to read what's called linear reading, which is line by line, row by row. In other words, in the printed format, our eyeballs are able to catch far more detail than we are on a physical screen. Key thought number 4, increasing finger usage increases brain function. For example, if you do things like you increase physically writing, specifically writing in cursive, okay, physically drawing, physically holding models and making models, all of that, whatever increases your hand usage as you learn, even physically making little note cards or ringlets of note cards, all of that increased finger usage increases brain function. This is where it's going to get a little technical, bear with me. Physically tracing and drawing in math diagrams increases comprehension. This is where I'm going to be talking about your brain is in your hand. Your brain is literally connected to your hand. And when it comes to math, increased finger usage, specifically what's called the eye fingers, which is your index finger and your middle finger, you are going to be activating a part of your brain. Let me get in here so that you can look this up. Again, if this sounds very technical, you and your parents can look it up. There's a part of your brain that's called the left angular gyrus. And this part of your brain perceives spatial, mathematical relationships. So the more you're using your fingers to trace, draw, shade, scribble on stuff, the more that part of your brain is going to be activated, and you're able to perceive and receive proper input in order to relate with physical math diagrams. This also is also for physical tables in physics, chemistry, and the like. Again, we're activating the part of the brain called the left angular gyrus. There's the technical article from the research, as well as the footnote. And what we're going to be using is something called finger gnosis, which is, gnosis means to know. It means to understand things through your fingertips. Super important. In a math class, okay, that's the best I can do for an eyeball there, folks. Your eyeballs do not perceive all info. You do not receive all your information through your eyeballs. Okay? You do not. You perceive a good chunk of your information, especially in this geometry class, not just through your eyeballs, but through your fingertips. Let's model this. I'm going to be using colors. You don't have to use colors, but I'm going to show you how to model this. Now, very important, we're going to learn how to what's called activate that left angular gyrus. When I say physically trace, it is super important that you actually do that. Ready? First, we finger track and read. Put your finger right there, folks. Right there. Finger, not pencil, finger. Ready? Put your finger there. Now read out loud, 3 body parts. In segment FD, the distance F to E is 6, and F to D is 18. Find DE. Now when you first read that, that makes almost no sense. Let's take it one step at a time. Ready? Okay. It said the distance F to E is 6, so we're going to physically trace F to E, and that's 6. I've accounted for that. F to D is 18, so F all the way to D, physically trace it, is 18. Find D to E. I'd like you to squiggle it. Find D to E. Now wait 5 seconds. 5, 2, 1. You probably just had an aha moment like, oh, this is so easy. Well, why is this such an easy problem? Is because you activated the left angular gyrus of your brain, and your brain perceived it's just a big segment minus the little segment, and ta-da, you get what you're trying to find, which is DE is 12. Let's try another one. Now we're going to get a little bit more complicated. Step number 1, again, finger right there, finger, not pencil. Read with 3 body parts. Read aloud with me. In segment GD, the distance F to D is 15, and F to E is 11, and G to E is 18. Find G to D. One step at a time. Ready? F to D is 15. So that's going to be F to D is, excuse me, let's keep my color straight here. F to D, so from F to D is 15. I'd like you to physically bracket it up here. It's a little bit easier. That's 15. F to E, that's a typo, let's fix that, is 12. F to E is 12. Physically trace that. And then here we have G to E, which is all the way from here, trace it, to here is 18. Your ambition is to find G all the way to D. I'm going to give you 1 minute on your own to see what you can do there all by your lonesome. 1 minute. Go back and physically trace stuff, see what you can do. 1 minute. All right, let's see. It's really important. Now, even though you're looking for the red, you should have first found, if that's 15 and 12, this little piece right here is 3. And then here, if from here to here is 12 and the whole thing is 18, from here to here is going to be 6. And then your ambition was to find the length of the entire segment. You just physically trace that. We already have that. From here to here is 6. Physically trace from here all the way to here to D is 15. So all you had to do was simply 6 plus 15, and you would have gotten 21. Physically trace stuff out. Let's try another one, using angles this time. We're going to trace and sweep the given information, trace and sweep angle B, find angle B. Our given information, let's just see what we have here. We have an angle, this angle is 115 degrees. Let's just physically trace it and sweep. Trace that 115, sweep the 115. Now you ask yourself, what else have you been given? You physically trace the diagram, a really simple concept. We've been given a straight line. I'd like you to physically trace that straight line. Now I'd like you to sweep that straight line. Now, I'd like you to physically trace and sweep angle B. You're going to find angle B. Go back, let's physically trace the 115. Physically sweep that straight line. Now physically trace angle B. 5 seconds. Your brain just had a flash of understanding. Solve for angle B. You have 30 seconds. Go. No calculators, kiddos. Keep your hands off that calculator. Okay, your brain registered that if this is a rainbow, it's 180 degrees. And all you had to do was simply subtract that 115. And you would have gotten 65 degrees. Let's try another one. Trace and sweep the given information. Trace and sweep angle B. Find angle B. Let's see what our given information is here. Our given information, first we have the 78 degrees. So let's just trace and sweep that 78. And then we have this larger than obtuse angle. Trace and sweep this. Trace and sweep angle B. That's what we're looking for. You're like, I have no clue how to find that. That's okay. Just keep physically tracing the diagram. For example, why don't you put your pencil right there? I'd like you to physically trace, go all the way around, keep going, keep going, keep going, keep going, keep going, physically all the way around. Just for giggles, do that exactly again. The exact same thing, pencil right there, go all the way around, all the way, all the way. Keep going, physically trace it, physically trace it, physically trace it, physically trace it. Wait 5 seconds. You just figured out how to solve for angle B, didn't you? Do the math in the margin. No calculators, folks. Keep your hands off those calculators. Okay, let's check. You should have added and figured out that 204, and then you did 78. We add, that's 12, carry the 1, that's 8, and that's 282. But then that green is 360 degrees. It's a circle. So we do 360, and you simply minus 282. And we get 78 degrees. Again, it's all about tracing, stretching, sweeping, shading. That's how your brain activates these diagrams. Now we're going to apply this to a little bit more complex problems. The number one problem for students overcoming complex problems is they think, I don't know what to do. I don't know what to do. And then they give up. What you need to understand is that you don't understand first and then apply effort. That's not how math works. You actually have to first apply effort and then, aha, you have understanding. In other words, effort yields understanding. Then the next question is, if effort's understanding, but I don't know even where to start, how can I give effort? This is 19 years of geometry experience here, folks, in one page. What can you do when you don't know what to do? 5 things. I'm going to walk you through it. Number 1, when you don't know what to do, you always start by reading with 3 body parts 3 times. You put your finger on the paper, lips moving, eyes on paper. That's round number 1. 2, you filter or highlight keywords, numbers, watch out for units. 3, you draw a label list, cross out. You physically trace and draw on your diagrams. This little icon means no naked diagrams. You should physically label, draw, trace, shade, stretch, sweep, all diagrams. You are physically interacting. Dress up your diagrams. 2, the 5 R's. Review your reference folder, recite recent revelations. You go to your reference folder, you flip through it and ask, what have you learned recently? Review reference folder, recite recent revelations. Review reference folder, recite recent revelations. Say it with me. Review your reference folder, recite recent revelations. That's the 5 R's. You ask yourself this question, a very simple but very important question. What can you do? You do not ask these should-do questions. Should stops your brain thinking, because the minute you don't know what you should do, you stop giving effort. So you ask yourself, what can you do? Squeeze the sponge means find everything possible. Squeeze out all the information that you can possibly find out of the problem. Number 4, when you're working with equations, there's an equal sign, and you always have 2 sides to that equation, not one. I'll show that to you in a minute. And last, when you work with equations, you're going to learn to do what's called circle, plug, chug. I'm going to model this for you for the next couple problems. But before we do that, we need to go ahead and learn to have translation words to math. Keywords in dealing with operations. Let's write these out. These should be familiar to you from prior classes. Addition. Plus. More. More than. Some. Minus. Less. Less than. Difference. Product. Times. And often the word of. Occasionally the word per. That's only occasional though. Division. Quotient. Divide. The word over, meaning something over something, implying a fraction. Often the word per is a division concept. Here's the most overlooked and by far the most important. An equal sign is the word is. And all variations are, was, were. Very careful with that. Occasionally the word total. Now, knowing this, let's come down here. I want you to take these phrases on your own, translate them to an expression or an equation, and then restart the video. You're doing this on your own. Pause. Welcome back. Let's see how you did. 5 minus 2 is 3. 5 minus 2 is 3. 6 times 2 is 12. 6 times 2 is 12. 9 more than the unknown is 15. 9 more than the unknown is 15. 8 more than the unknown is 20. 8 more than the unknown is 20. Twice the sum of 4 and an unknown is 10. Twice the sum of 4 and an unknown is 10. Be very careful because of that word sum there, we have ourselves a set of parentheses. Last one, half of an unknown less 8 is 16. Half of an unknown less 8 is 16. You should be correcting those in red pen. If you're correct, some sort of smiley face, star, woohoo, I got it right. If you got something wrong, figure out why. Now, let's apply this to a couple problems. Let's recap, though, two main equations that we're going to work with in geometry is the perimeter and the area of a rectangle. Very simple. You've seen this before, most likely. But I have some things I want you to remember. When you are working with perimeter, always physically trace it. Physically walk it around, and you're going to imagine that you're walking around a picket fence. Perimeter, picket fence. Let's label your lengths and your widths. And when we walk this around, it's a sum problem. So it's simply going to be length plus width plus length plus width. I'd like you to write that down. Now, because we have two lengths and we have two widths, in textbooks, they write them like this, and this is perfectly fine, but make sure you don't drop the plus sign. Perimeter of a rectangle equals two lengths plus two widths. Perimeter, picket fence. You always physically walk it around. Area. I want you to get in the habit when you're dealing with area, I'd like you to physically shade. Shade the area. Physically shade it. And to find the area, imagine laying grass. Grass is area. Perimeter is picket fence. To find the area of a rectangle is simply length times width. Let's put this to use using our brain and hand techniques. Ready? 3 body parts, 3 times. Put your finger there, right there. Read out loud with me. The perimeter of rectangle PQRS is 26 centimeters. The side PQ is 3 centimeters longer than QR. Find the area of the rectangle. That's pass number 1. Let's filter. We got ourselves a rectangle. The perimeter of the rectangle is 26. Instantly, the minute you see is, put an equal sign right above it. We have a side length, which is 3 centimeters longer than the other one. And our ultimate goal, I always like to box the ultimate goal, box it, question mark, area. That's 2. Draw label list, cross out. Ready? PQRS. Put your pencil there. P, Q, R, S. Why did I go this way? Because I know that side length PQ has to be longer than QR. So QR is a shorter side, PQ is the longer side. PQ is 3 centimeters longer than. So this is X. That means longer than. That's a plus concept. So this is X plus 3. We don't know this, but this is X plus 3. And what I do know is that the entire perimeter is 26 centimeters. Ready? I've accounted for the rectangle. Cross it out. I've accounted for the perimeter being 26. PQ, 3 centimeters longer than QR. You're like, I don't even know where to start. Well, you always ask yourself, what could I do? Well, I have perimeter. Can you write the equation for perimeter out? Sure, that's easy. So let's write it out. Perimeter equals 2 lengths plus 2 widths. I'm going to be working with area, so can I at least write the equation for area out? Sure, let's write that down. Area equals length times width. Ready? Now start circling stuff that you know goes together. For example, do you see that P there? I'd like you to physically circle it. That's perimeter. Come up here, physically circle it. Oh, perimeter. That means I can circle and I could plug that 26 for that P. So we're going to write that down. 26 equals. Ready? Let's circle that L. That's length. Come up here. Oh, I could substitute that, circle it, for this. Plug it in. Careful with that too. Plus, circle W. What do I have going for W? Come up here, physically circle the X, plug it in. Fabulous. Now we're down to one variable. Let's solve for X. Do your own math. Ta-da! We just found X equals 5. Again, our goal here is to find our area, which is length times, whoops, my time sign looks like a plus sign. Let's go ahead and use a parentheses there so we don't do that again. Length times width. So now let's take the X and plug it in. Wherever you see X, circle, plug, chug. So we're going to plug in 5 here. And this becomes obviously 8. So now we're going to circle, plug, chug here because now we have our lengths and widths. Let's circle our length, physically trace our length. We just figured out that our length is 5 plus 3 and we have an 8 here. Physically circle the W, come up here, trace it. Oh, that's 5. My area is going to be 40. We check for units. Our units are centimeters, and because area is 2 dimensions, this is going to be centimeters squared. Let's try another one. This is all new to you. But learn to use those 5 steps. Teacher example. Number 2, we're going to read with 3 body parts 3 times. Ready? The area of PQRS is 48 centimeters squared. The side length PQ is 3 times the length of QR. Find the perimeter of the rectangle. That was pass number 1. 2, let's filter. Highlight key things. We're dealing with area, and the area is 48 centimeters squared. One side is 3 times longer than the other. Our ultimate goal is to find the perimeter. Now, number 3, we draw a label list, cross out. So we're going to draw. We have PQ, RS, and again, our PQ has to be longer than this side. So I'm going to start right here. Clockwise, not zigzag. And I label. PQ is 3 times, that's 3 times the length of QR. We don't know QR, we'll call that X. That means PQ is going to be 3X. We are given the area. Let's shade the area. Always physically shade the area. Let's write down what we have. Area equals 48 centimeters squared. We ultimately want perimeter. You ask yourself, what can you do? Find everything you can find. Well, let's see, we're working with area. We could easily write the area equation. That's easy. And I could very easily write the perimeter equation. That's something I can do. It doesn't require any thinking whatsoever. You do what you can do. Now let's start circle, plug, chugging and see if we can connect anything. For example, that area there can swap out for that area. So we're going to swap the 48 and stick it right there. Circle the length. Oh, we have a variable for that. That's 3x. Circle the width. We have a variable there. Let's get closer. Very important. X times x is x squared. We're going to solve by dividing. 3 goes into 4 one time, 1 left over. 3 goes into 18 6 times. The opposite of squaring is square rooting, not dividing by 2. Fabulous. I just found what x is. Let's see what we can do within it. Circle, plug, chug. So we just found if that's x, that means this side length here is 4. Plug it in. That's 4. This side length here is 12. Our ultimate goal is to find the perimeter, so let's circle, plug, chug. Perimeter, circle it, we don't know. 2 parentheses, circle the L. 12 plus 2, circle the W. Do your own math. So our perimeter, given these circumstances, is going to be 32. You check for units. If area is centimeters squared, perimeter is only one dimension, so it's just centimeters. I know this has been a little bit longer, but this is one of the most important lessons of the entire year. Take about 2 to 3 minutes to read this, 3 body parts 3 times. Pause the video, attempt to do this completely on your own, and then restart. Go. Pause. Don't copy, students. Do this on your own and then restart the video. Have a red pen in hand. All right, welcome back. 3 body parts, 3 times. So we have Miss Johnson wants to plant a flower marigold border around her small herb garden. The herb garden is rectangular, and the length of the garden is 3 times longer than the width. Area of the garden is 108 feet squared. It will take 3 pots of flowers per linear foot to create the desired border. The flowers cost $2 per pot. How much will it cost to plant the marigold border around the herb garden? Don't worry about tax. Ready? Filter. Keywords here. It's a border that we're working with. It's rectangular. The length is 3 times longer than the width. We have the area. We have 3 pots of flowers per linear foot to create the border around the garden. Flowers cost $2 each. Now we're going to do what's called draw, label, list, cross out. Draw, label, list, cross out. So first off, it says right here, the length is 3 times longer than the width. So this is our length is 3 times longer than the width. Whatever the width is, our length is 3 times longer than our width. We've got that taken care of. The area we've been given, the area is 108 feet squared. When we want to plant the border, we're going to have 3 pots of flowers for every linear foot. So for every 1 foot, we want to buy 3 pots of flowers. Notice I'm making physical diagrams. 3 pots of flowers for every 1 foot. That's for the border. And they cost $2 each. And I'm asked, the ultimate question is border. If we're going to deal with border, what we're ultimately dealing with, let's physically trace the border, physically trace it. You should have figured out that border is code for perimeter. So we come over here, don't know what to do. Well, we can at least write our equations out. Circle, plug, chug. Watch what I do. See if you did the same thing. Replace the length with 3W. The width is already W. This is 108. We have W squared equals 36. The opposite of squaring is square rooting. You should have figured out that your width here is simply going to be 6 feet. So let's plug this in. Our width is 6 feet, and that means our length is going to be 3 times 6, which is 18. Come down here, let's find our border. 2, circle the L. 18, we plug it in. Circle the W, plug it in. This is going to be 36 plus 12. And we figure out that our perimeter is going to be 36 plus 10 is 46 plus 2. We have 48 feet. Now for every foot, we're going to buy 3 pots of flowers. So 48 times 3. And that's 144 pots I am buying for my border. And they cost $2 each. So cost-wise, you simply double it. You should have gotten $288 for the marigold border. Check your work, red pen.